All right, so in this section, we're going to solve trigonometric equations by using trigonometric identities. And this is one of the main purposes of trigonometric identities just in general. There are other reasons that we use trig identities, but to solve trig equations is definitely one of them. Remember, if we're using math to try to explain the world, whether it's in science or in another area, it's not our choice whether natural phenomena happen to behave according to trigonometric equations that are easily solvable or not. Sometimes a phenomena, say, let's take tides is a common one. The height of a tide does follow a fairly a trig equation that's fairly easy to solve, but some phenomena don't. So we use identities to transform those equations into equations that can be solved. And by the way, there are also equations that just literally cannot be solved. Those are called intractable. And then we use other techniques. Usually we use computers to help us solve those types of problems. So here's an example. We're going to solve for x. We have cosine of 2x plus 1 minus cosine of x equals 0. Notice that double angle jumping out at us. So I'm thinking double angle identity immediately. And, I'm already, before I even start going too far, I'm immediately scanning my mind. What are my options? I have cosine x squared minus sine x squared. I have 1 minus 2 sine x squared, 1 minus 2 sine x squared. I have 2 cos x squared minus 1. And I'm keying in on this one right here because it is cosine of x squared that I have, and that matches this cosine of x. Okay, so my first step here is to use that identity. I'm going to go ahead and say, all right, cos 2x is the same as 2 cosine of x squared. I'm going to write it this way just to be really explicit that we have the cosine function itself being squared, minus 1. And then I have a plus 1. And then I have a minus cosine of x equals 0. And I have my restriction here. Now, cosine is never undefined, so I don't need to worry about restrictions here. I can just solve this. We have minus 1 plus 1, so those so-called cancel. We have two groups of cosine x squared minus cosine x equals 0. All right, this is not a difficult situation. If you prefer, you can quickly let u be cosine x squared and see how do we solve this? Well, we'd factor out a u, and we'd have that, and we'd say, okay, well, the only way that the left-hand side can be 0 is if u is 0, or if 2u minus 1 is 0. I'm going to do exactly the same thing. I'm not going to actually use this dummy variable here. I'm going to do it directly because I can do that much work in my head. I'm going to factor out my cosine x. So I have cosine of x here times what's left? Well, two groups of cosine x minus 1 equals 0. How can that equal 0? Well, if cosine of x equals 0, or if 2 cosine of x minus 1 equals 0. So I'm going to solve both of these equations under 0 is less than or equal to x is less than 2 pi, so 1 full revolution. Cosine, I can do it in my sleep, right? I've memorized what cosine looks like. I don't even need to sketch in that curve there. I've got pi over 2 and 3 pi over 2. So I have x is pi over 2 and 3 pi over 2 for 1 revolution for x between 0 and 2 pi. And here, this one I can solve as cosine of x equals 1/2, special angle. So, as you get more and more practice with these, you can go pretty quickly. You don't even need to sketch out your graphs. You can just start writing down the solution. I'm going to continue to sketch out the graphs, of course, because I'm teaching it and I don't want to leave anyone behind. So here I have cosine of an angle is 1/2. That's a special angle. That's pi over 3 or 60 degrees. and I have ASTC, cast, or whatever acronym you want to memorize that. And so since this is a positive 1/2, I'm going to use this quadrant and this quadrant here where cosine is positive. I'm not going to use those two quadrants. So I get the solution pi over 3 because that it gives us 1/2 cosine of pi over 3. And then I also get this angle right here, which is equal to 2 pi minus pi over 3. Or in other words, 5 pi over 3. And there we have it. Okay, so I bring these together. My solution then is x equals, and I'm going to try to put these in order. I guess pi over 3 comes first, then comes pi over 2, then comes 3 pi over 2, and last comes my 5 pi over 3. Done. Now in this section, I'm just going to walk through several examples where we're using trig identities to solve trig equations. All right, so here's a question. I'm looking at it. I'm going to talk through what I'm thinking, okay? I'm thinking I've got cosine of x and sine of x. I need to somehow get those to both be the same thing. I do not have a double angle here. So all the double angle identities are not going to be helpful to me. Some difference, those aren't going to be helpful. I need to be looking at reciprocal, which won't be helpful because there's no cosecant, cotangent, or secant. Looking at Pythagorean identity, that looks good to me. This is looking like a Pythagorean identity situation, or something else. So I keyed in on the Pythagorean because anytime you have a 1 minus cos squared or 1 minus sine squared, or something of that nature, you can start thinking Pythagorean identity. I'm going to put over here that we have sine x squared plus cos x squared is 1. That's the Pythagorean identity in its original form. And so that says that 1 minus cos squared is sine squared, sine x squared. So this here can be replaced by sine x squared. And I'm immediately seeing, yeah, this is going to work out because sine x squared and sine x and some constant looks like some sort of quadratic, right? So I'm going to subtract 3 sine x on both sides. I'm going to add 2 on both sides, and I get this equation here. Okay, now I'm going to write a line that is completely optional, but just to make it super clear, this is a sine x squared. I'm just clarifying what that notation means. Okay, and again, completely optional, I'm going to let u be sine of x, just to make this look nicer. That makes this a u squared minus 3u plus 2 equals 0. Okay, now I can factor. What two numbers multiply to positive 2, but add to negative 3? Well, that would be negative 1 and negative 2. Those add to negative 3 and multiply to negative 2. I can double check. It looks good. And now I'm going to substitute sine of x back in for u. So I have sine of x minus 1, sine of x minus 2 equals 0. Okay, actually I should do that one in light blue. Let me just quickly fix that. Because at this point I have something that once you get some practice, you could jump straight to this step. Okay, straight from the first light blue to the second light blue. Because you can look at that first light blue there and say, okay, this is a quadratic. Sine x is my u. I'm looking for two numbers that multiply to negative 2 and add to negative 3. Plunk them in, and you can build it and then double check that it works. Okay. So now at this point, I'm saying, well, how can the left-hand side be 0? Well, the only way for the left-hand side to be 0 is if this is 0 or this is 0. So I have sine of x minus 1 equals 0. I have sine of x minus 2 equals 0, and I need to solve both equations. I have sine of x equals 1. I have sine of x equals 2. Now this is interesting. When does sine of x equal 2? What's the max of sine x? Well, the max of sine x is 1, right? This is our picture of sine x. The max is 1. The min is -1. It has an amplitude of 1. Sine x is never 2. So this here will not give us any solutions. There's no solutions there. Maybe we could even put no solutions from this part. So the only solutions to this entire equation are going to come from this part right here. And this, well, I just sketched it out right here. When is sine of x 1? Right here at pi over 2. That's the only time in one revolution, and we were asked to do it for one revolution. It's the only time that sine of x is 1 at pi over 2. So that's our final answer. X equals pi over 2. Okay, here's one with a double angle, and it's the sine double angle, which only has a single option for the double angle identity. So I'm just going to go ahead and do it. This is 2 sine of x cosine of x. I don't really have much choice here, seeing as how this argument is x and this one is 2x. That's pretty much my only choice. It's my only reasonable choice. And so now I think, what could I do? Well, I have a cosine of x in each term, so I'll factor that out. That should be the natural gut reaction. Whenever you're trying to solve and you have a common factor, you factor it out. So I factor out my common factor of cos x. I'm left with 2 sine x minus 1 equals 0. And the only way for this to equal 0 is if cos of x equals 0 or 2 sine of x minus 1 equals 0. Okay? I could have used a dummy variable if I wanted to, but I don't need to, so I'm not going to. Okay, now cos of x equals 0. Pretty simple. We're going again over one revolution. So when is cos of x 0? Right here and here. Pi over 2. That looks like a face. And 3 pi over 2. Okay? If I needed to sketch it in, there it is. Here I have sine of x equals a half. When is sine of x a half? Well, we know for sure the special angle, pi over 6, that's 30 degrees. And then we can just do it. ASTC, I want this quadrant because it's positive, and this quadrant because it's positive. I don't want those quadrants. So I get pi over 6 right here. And my other angle is 180 minus pi over 6. Or I guess I should say pi minus pi over 6. So I do that calculation, right? This is 5 pi over 6 because this is the same as 6 pi over 6 minus pi over 6, which is 5 pi over 6. So my two solutions here are that x is pi over 6 and 5 pi over 6. My two solutions here are pi over 2 and 3 pi over 2. And now I just list them out in order. Pi over 6 is the smallest, then comes pi over 2, then comes 5 pi over 6, and last but not least, 3 pi over 2. That's it. Now feel free for any of these to pause the video if you want and try it out on your own, and then see if you get the same answer as me. It's always good to actually try to do it yourself rather than just passively watching a video. And I'm just going to carry on. I've got maybe 4 more examples or so, and I'm just going to run through them. Okay, so this is an interesting question. I see the sine x squared, and I'm thinking Pythagorean identity. I'm seeing the 2 cos x. Well, I'm not really thinking much of anything. Yeah, I'm thinking Pythagorean identity. If I can change this sine x squared into something involving cos x squared, then the entire equation will be in terms of cos x, and I'll be able to probably factor and solve that way. So over on the side here, I'm going to quickly remind myself that sine x squared plus cos x squared equals 1. And so if I subtract cos x squared on both sides, I can replace this sine x squared with 1 minus cos x squared. I have to be a little careful because of the subtraction there. So I'll put brackets, and that's what I'll do. So I have 2 cos x plus 1 minus bracket 1 minus did I say, yeah, cos x squared. Just about put a sine x squared there. Cos x squared equals 3. Alrighty. Now I'll distribute my brackets. So I get, well, you know what? I can rearrange as well. So I have 1 minus 1. That's going to go. I have minus minus. That's going to be positive cos x squared. So I'm going to write that first. I might as well start rearranging my terms in the right order. I have plus 2 cosine of x minus 3 on both sides equals 0. And now I'm factoring, right? If I wanted to, I could, I could say let u equal cosine of x, and I'd have u squared plus 2u minus 3 equals 0, and I would go ahead and use the techniques from Math 10, I guess it is, maybe even Math 9, depending on your teacher, I guess. Or I can just go straight up and just use cosine as it is. That's what I'm going to do. I'm looking for, well, there's no a here. There's no coefficient on the cosine x squared. So I'm going to, whoops, that was a mistake. I don't want a squared there. So I have cosine and cosine. I want two numbers that multiply to negative 3 and add to positive 2. So the 3 must be the positive one. Double check. Cos x times cos x squared. This is plus 3 cos x minus 1 cos x. That's the same as plus 2 cos x minus 3. We're good. Okay, the only way for this to equal 0 is if each part equals 0. So I have cosine of x equals 1. I'm skipping one step here. And cosine of x equals negative 3. Now this is interesting because we can never have cosine of x equal to negative 3, right? I mean, if I had some coefficient in front of cos x, well, then I could have a negative 3 perhaps if I had a vertical stretch, but there is no vertical stretch. The minimum of cosine is negative 1, so there's no solution coming from this part here, okay? But I do, of course, have a solution coming from my cos x equals 1. I'll just come over to the side. I've got this memorized. Here's cosine x over 1 revolution. I get cosine x equals 1 at 0. No. And then again at 2 pi, but I have to be very careful. I'm being asked for the solution between 0 and 2 pi, including 0, because it's less than or equal to, but not including 2 pi, because it's strictly less than. So for this, my solution is x equals 0. That's my final answer. Technically, if I put x equals 0, 2 pi, that would be wrong, because the domain that I'm being given here does not include 2 pi. It goes just up to, but not including 2 pi. So there's my solution, x equals 0. All right, this is a nice question. So I'm looking at it, I'm seeing the cotangent that's jumping out at me, and I'm thinking I'm going to put everything into sine and cosine and see if that helps. So cotangent is cosine over sine. That will be my first step, cosine over sine. And lo and behold, look, it does help because the sine cancels out. That's nice. Now I have to be a little bit careful here. Here now, I have cotangent, which is cosine over sine, gives me a denominator of sine, and we can't divide by 0. So I'm going to get some restrictions. Let's go ahead and get those restrictions before carrying on. The restrictions here are going to come from sine of x cannot be 0. If sine of x is 0, then cotangent of x is undefined, and we have a problem. So this isn't too hard to solve because, of course, we've memorized sine looks like this. So Sine is 0 when x equals 0, so x can't be 0. And sine of x is 0 when x equals pi, so x can't be pi. Sine of x is also 0 when x is 2 pi, but if you look closely at this domain, 2 pi is not included. So we don't really have to worry about 2 pi as a restriction because it already should be rejected in the end. It's not going to be part of the solution. So my restrictions here are x can't be 0 or pi. All right, let's get back to the actual question here. I'm going to be able to so-called cancel out, right? Because this is cosine times sine over sine. Divide top and bottom by sine, we get cosine. So now we have cosine of x equals cosine of x. Oh, how interesting is that? How interesting is that? So you might be looking at this and be a little bit stumped, but you have to think, what is the meaning of an equation? An equation means when it says solve for x, which is, I didn't write it here, solve for x, but that's really what's being asked of us. We're trying to find all the values of x over the domain, and we're given this is the domain that we pay attention to. We need to find all the values between 0 and 2 pi that make the equation true. When is this equation true? It is always true. So if I look at this equation, just this one right here, I would say x is all real numbers. Or more precisely, because I have a domain that I'm supposed to work over, I would say x is all the values between 0 and 2 pi, including the 0 but not including the 2 pi, because that's what I'm given. However, I also have these restrictions. So in fact, my final answer is going to be all the x's between 0 and 2 pi, including the 0, except not x equaling 0 and not x equaling pi. This is the solution. What a fascinating question. Okay, I could write this another way, and I will actually. If I want to exclude 0, instead of writing it explicitly, I can very easily just drop this or equal to. So I could also write this solution as 0 is less than x is less than 2 pi, and x is not pi. That's an equivalent solution, which I think looks slightly nicer. But they're both right. They're both correct. Isn't that fascinating? Let's cash this out a little bit. This means if I take any value between 0 and 2 pi, as long as it's not pi, and plug that value in here, here, and here, I get a true statement. I get that the left-hand side equals the right-hand side. Let's try it out. Let's pick a special angle or two that we like and just verify that this is true. Let's take, I don't know, let's take x equals pi over 4. I like that one. Pi over 4, so we have cosine of pi over 4 squared equals cotangent of pi over 4 times sine of pi over 4. Cotangent of pi over 4 times sine of pi over 4. Of course, we could use a graphing calculator or even a scientific calculator. We could use a computer. We could evaluate over all of these values actually fairly quickly with a computer if we wanted to. But I'm just going to do it by hand here. So I have cosine of pi over 4. Now cosine of pi over 4 is 1 over root 2. So we have 1 over root 2 squared. Cotangent of pi over 4, well, that's the same as cosine of pi over 4 over sine of pi over 4 times sine of pi over 4. I'll evaluate that one. That's also 1 over root 2. And we have that this is, oh, now hold on for a second. Now, would you look at this? So I made a mistake. And it's actually, this is really instructive. So I'm going to leave this here. You know, I could chop it out of the video, but I won't. This is really instructive. Can you find the mistake? Pause the video here and just see if you can find the mistake. Maybe you already saw it. Okay, so first of all, how did I know I made a mistake? Because I decided to check a value and see if it's true. Always worth doing. If you have the time, check a value. See if it's true. See if your solution makes sense. So I did that, and I stopped right here because I was like, wait a second. This is going to cancel with this. So I'm going to have cos of pi over 4, which is 1 over root 2. But on the left-hand side, I have that squared. That's 1 over 2. This is not true. So that means that this is not a solution. So that means that this is not the right solution. Okay, so then there must be a mistake somewhere. And I'm looking at this and I'm thinking, wait a second, if I didn't square it, then it would be true. I wonder if I forgot a squared somewhere. And so then I scrolled back up. You can actually look back at the video and see I literally scrolled back up quickly. Oh my goodness, I missed the squared. So all of this is correct. I just did the wrong question. Okay, let me do it again now that I've got the right question and solve the right question. This was a very nice question. The wrong question was actually really nice. I liked it. But let's solve the right question here. Okay, so here we go again. Now, I'm going to be very careful here to write the cos x squared. And my cotangent is cosine of x over sine of x times sine of x. And actually, you know, I know why I made the mistake. It's not an excuse, but it's because on my version, I have all my pens here, and they cover up the squared. Anyway, and so I get the restriction because I can't divide by 0. So sine of x cannot be 0. I go and I look, well, this is what sine of x looks like. So I can't have an x of 0. I can't have an x of pi. I can't have an x of 2 pi, but I don't need to worry about that because it's not part of the domain anyways. So I don't really need to restrict it here because it's already restricted up there. So that's fine. I divide numerator and denominator of this whole fraction by sine, thereby canceling the signs, so to speak. And so now I'm left with cosine of x squared equals cosine of x. And how do I solve this? Well, I will subtract cosine of x on both sides equals 0. You know, this is very similar to how would you solve this? And actually, I should point out a lot of students, I find they do not solve this correctly. They're tempted to just divide both sides by x to get x equals 1. That is wrong. That is wrong because you lose a solution. If you do that, you get x is 1, which is true, but you miss out that x is also 0, right? 0 squared equals 0. What happened here? Well, the problem was you divided both sides by your variable. You don't want to do that. You'll lose solutions. What do you want to do if you have x squared equals x? You want to subtract that x on both sides and then factor it out. Okay, now you have, well, how can this left-hand side equal 0? Well, if this equals 0 or this equals 0, and that's how you get both of your solutions. Okay, very, very important. So same thing here. I have cos x squared equals cos x. I do not want to divide both sides by cos x. I'll lose a solution, or possibly many, because cos x, of course, could have more than one solution. What do I have to do? Subtract cos x from both sides. Now I can factor out my cos x, and I'm left with cos x onto cos x minus 1. Now, if you want to use a dummy variable, you could. In fact, the whole dummy variable approach is right here in purple. So I've got this here. Now, how could that equal 0? Well, or if cosine of x minus 1 equals 0, these are the two ways that this expression here could equal 0, if cos x equals 0 or cosine of x minus 1 equals 0. This I'm going to solve in a second. This, I'll just go one step further, add 1 to both sides. Here we are. And I can solve both of these just by looking at this sketch here. Cosine starts high, crosses here, goes low, crosses here, comes back up here. It looks like that. And so for what x's is cosine of x 0? Well, here and here. That's pi over 2 and 3 pi over 2. For what values of x is cos x 1? Here and here, but again, this is not part of our domain. So the only solution from this part here is x equals 0. Let's look now. Do I have restrictions? I do. I have to restrict. X cannot be 0 or pi. So I have to reject. Let's cross it out like that and just write the word reject. I have to reject this solution. This solution is not valid because of this restriction here. Okay? So I don't actually end up getting any solutions on this side. My final solution is that x equals pi over 2 or 3 pi over 2. That is it. Okay, here's an interesting one. I have a root 2 in there. It shouldn't really cause any concern. I'll just treat that like any other number. I have the same domain that I'm working over. 0 less than or equal to x less than 2 pi. That's pretty common. It's one revolution. And I have a sine 2x. Well, there's really only one thing to do with a sine of 2x, and that's to write it as 2 times sine of x times cosine of x. So that's pretty straightforward. And then I'm looking here, so everything, well, no, that's not true. It's not all in terms of cos x. I have the sine x as well. Well, maybe if I subtract root 2 cos x on both sides, I'll be able to factor something out. And in fact, I can see that I can factor something out, and that's going to be nice. By the way, there are no restrictions here, right? I'm not dividing by anything. I'm not square rooting a negative. This is just a root 2. It's just a constant. So there's no restrictions to worry about. Now, I can factor out a cosine of x, and I'm left with 2 sine x minus root 2 equals 0. That's interesting. Okay. And so how could that equal 0? Well, if cosine of x equals 0, or if 2 sine of x minus root 2 equals 0. So I solve each of these. The cosine x is pretty straightforward. It's going to be this picture here. So when is cosine x 0? Pi over 2 and 3 pi over 2. This one here, well, I'll add root 2 to both sides and divide both sides by 2. This is root 2 over 2. Okay, now some of you are going to look at that and say, oh, I know what that is. This is a special angle. Some of you might need a little bit more convincing, and that's okay. So root 2 over 2 is the same thing as 1 over root 2. How is that? Well, this is the same as root 2 over root 2 times root 2. Root 2 times root 2 is 2. And then we could divide top and bottom by root 2, getting 1 over root 2. Okay, this and this are identical. So some people memorize their special triangles using root 2 over 2. Some memorize them using 1 over root 2. Some memorize them using both. In fact, that's probably optimal because then when these different situations come up, you're prepared for them. Regardless, we know what to do. So I'm going to sketch out here. I know that I have pi over 4 or 45 degrees. That's the reference angle for root 2 over 2 or for 1 over root 2, right? It's this picture like this. Sine of 45 degrees is 1 over root 2. And then I have to see here, well, it's a positive. So since it's positive, I'm going to use the first and second quadrants. I don't want the third or fourth quadrants because sine would be negative there, but I'm given this that the value has to be positive. And then what's the corresponding angle in second quadrant? Well, it's pi minus pi over 4. That's going to be 3 pi over 4, right? Pi minus pi over 4 is the same as 4 pi over 4 minus pi over 4. That's the same as 3 pi over 4. So from this, I get that x is pi over 4 and 3 pi over 4. Well, I just bring it all together now, and I always try to write them in numerical order. X starts with, I guess, pi over 4 is the smallest, then pi over 2 is the next, then 3 pi over 3 pi over 4, and then 3 pi over 2. There we are. Those are the values for x that work. And you know, if I wanted to check one of my solutions, it wouldn't be the end of the world. It's not a bad idea, especially if I have extra time sitting on a test. Throw one of them in. Now, I'd have to be careful, though, that I put in something that I can evaluate. If I put in pi over 4 right here, yes, I can evaluate it. But if I put in pi, well, I guess I could evaluate that too. 2 times pi over 4 equals pi over 2. I could evaluate that. So that would work, actually. I could do it with pi over 4. Is there one here that might not work? Actually, these should all work. So that's fine. So why don't I do it? I'll do it with pi over 4. Sine of 2x equals root 2 cos of x. I want to see, is this true? This is my check. And let's see here. So I'm going to use x equals pi over 4. So I have sine of 2 times pi over 4 equals root 2 times cosine of pi over 4. This is saying sine of pi over 2 equals root 2 times, well, cosine of pi over 4, I can actually do that now. That's going to be 1 over root 2, or root 2 over 2, right? See, I actually pick 1 over root 2 here because I can see it's going to cancel with this root 2. If I had some other expression, I might have picked the other form, the root 2 over 2 form. So this is going to cancel out and make 1. And what's sine of pi over 2? Well, it is 1, right? So that's good. So it shows that it works. And if we really wanted to, we could check with the other solutions too. Okay? Okay, last one here. So this one looks kind of interesting. I have a sine and I have a cosecant. And cosecant is 1 over sine. So that matches up. I don't have any double angles. So I think I'm just going to literally use the reciprocal identity that cosecant is 1 over sine. And I think that will probably be good. I have some kind of interesting numbers here. That 7 scares me a little bit, but let's see what happens. 2s and 3s I'm a little bit more used to. So cosecant is 1 over sine. That's fine. Now I've got a restriction, right? Cosecant has some values of x for which it's undefined because cosecant is 1 over sine and you can't divide by 0. So I'm going to get restrictions here that x can't be 0 or pi. How did I get that? I quickly sketched this in my head and said sine of x is 0 when x is 0 or when x is pi, or when x is 2 pi, but I don't need to worry because that's not even part of our domain. Okay, so these are my restrictions. What am I going to do here? Well, you know, sometimes when you have a problem and you're not quite sure what to do, it's helpful to think of a similar problem and think, what would you do there? What if it was just 2x equals 7 minus 3 over x? What would you do there? Well, what I would do is I would multiply through by x. And multiply by x, multiply by x, multiply by x. Then I'd have a quadratic. I could bring everything over to one side and solve. So I'm going to do exactly the same thing here. Now, if you want to use a dummy variable, go ahead. There's no problem with that. You could let u be sine of x. I'm going to work through this without the dummy variable, okay? But I'll just be nice and careful as I go. So I'm going to multiply through by sine of x. If I multiply the left-hand side by sine of x, I get a sine of x squared. If I multiply the right-hand side by sine of x, I have to multiply every term by sine of x, so I get 7 sine of x. And the last one, when I multiply by sine of x, that just becomes 1 times 3. So there we are. So that looks fine. And I'll tell you what, I'm also feeling much more comfortable about the 7 now that I see it this way. Because now that I see it this way, I'm just thinking, oh, we are just going to factor a quadratic. And have I seen the number 7 when I'm factoring quadratics? Sure, that's not so scary at all. Not a big deal. So here now, again, you could use a dummy variable if you want, but I'm gonna forgo it. I'm gonna make my brackets, and I'm gonna say what two numbers multiply. Well, actually, what I'm gonna do is I'm gonna do guess and check, but then maybe I'll do it a second way. So I'm gonna actually just write out what two numbers multiply to make 2 sine x squared. Well, one of them has to be 2 sine x, the other one has to be sine x. That makes 2 sine x squared. And to multiply to get 3, there's only one way to multiply two numbers to get 3. That's 1 and 3. So the only question here is, what goes where? Now, first of all, to get a positive 3, they're either both positive or they're both negative. This is negative. So, in fact, they're both going to have to be negative, because if they're both positive, then everything remains positive and I won't have a negative 7. So it's actually kind of dictated for me. This is what I need to do. Now, here, let's double check. I have 2 sine x squared minus 1 sine x minus 6 sine x. That's my minus 7 sine x plus 3. That's it. If I put them in the wrong order, if I put the minus 3, whoops, that's a funky 3. If I put a minus 3 here and a minus 1 there, I just catch it when I multiply through, because I'd have minus 3 sine x minus 2 sine x. That's minus 5. It doesn't make the 7. So that's it. If you weren't comfortable doing it this way, you could do it another way, right? If I had, let's use a dummy variable here. Let's just suppose I have 2u squared minus 7u plus 3 equals 0, and I want to factor. I could also use the method where I multiply a and c, that's 6, and I copy down b, that's negative 7, and I ask myself, what two numbers multiply to positive 6 and add to negative 7? And I get negative 1 and negative 6. And then I rewrite the middle term in terms of the negative 1 and the negative 6. I get the GCF of the first pair. I get the GCF of the second pair, minus 3, like that. And now I have a binomial that itself is a GCF. There we are. And this is this factored. And of course, oh, hold on here. Did I make a mistake? I was going pretty quick to save time, and maybe that's cost me time. Let's see here. That's 2u squared minus 2. Yeah, I got the minus 5 case. Hold up, hold up. Hold your horses. Yeah, oh, I see what I did. I just, okay, let me back up here. I went too fast trying to save time. This isn't true. This is 2u squared minus 2u. That's not true, and this one isn't true either. So let's just erase a couple lines here. You know, sometimes when you try and go fast, you actually end up going slower. That's a good life lesson right there too. So here I have a u as a common factor. Okay. especially when I'm doing a video, you know, if you already know this, you can just fast forward. Why am I trying to go so fast? And here, what's the common factor? It's 3. So I'll factor out a 3. I'm left with, well, now hold on here. If I factor out a 3, this is negative 2u, but that doesn't match. So what I want to do is factor out a negative 3, and then that will give me a positive 2u. So that's negative 6u. And then a negative 1. That works. Let's double check. U times 2u, 2u squared, u times negative 1, negative u, good, negative 3 times 2u, negative 6u, good, negative 3, negative 1, positive 3, good, okay. So this works. And factor out the 2u minus 1, u minus 3 equals 0. There we go. And now this matches this, this matches this. There we go. But of course, as I showed you, I was actually able to solve it without any of this stuff here. But I just wanted to show you in case you weren't able to do it or you had another question where it wasn't as easy, so that you're reminded of this technique for multiplying trinomials where a is not 1. All right, so back on track here now. I'm going to say, well, how can I get this equal to 0? Well, only if 2 times sine of x minus 1 equals 0, or sine of x minus 3 equals 0. So I'm going to solve both of those equations. I get sine of x equals a half. I get sine of x equals 3. When is sine of x going to be 3? Never. I get no solutions from this one because the maximum of sine of x is 1. When is sine of x a half? This one I've memorized. I can just write it straight up. So I have pi over 6, but I'll draw my little picture. I'll draw it just right here. There's pi over 6, or 30 degrees. That gives me 1/2. Here we are. We've got our acronym. And so the other positive 1/2 is in this quadrant here. So it's going to be 5 pi over 6. It's going to be pi minus pi over 6, which is 5 pi over 6. So altogether then, I get x equals pi over 6, 5 pi over 6. I'm going to check to see if I have any restrictions, which I like to do in red, so they stand out. 0 and pi are my restrictions. No, those aren't included, so that's fine. Now, if I'm writing a test, I might just say, you know, restrictions checked or something, because your teacher has no idea whether you got the right answer because you checked your restrictions and didn't reject anything, or because you completely forgot to check your restrictions. So I like to include that just so that my teacher, my prof, knows that that I've checked, and that's it. All right, so we've got some good practice questions for this in the textbook, page 320, 1 to 5, 8 to 12 plus.